In this video, we'll be learning how to solve a system of nonlinear equations by utilizing the graphing strategy. So just as this sounds, we'll be creating accurate graphs of linear and nonlinear equations in order to find their points of intersection. So in this first example here, you'll notice we have two equations. This first equation is a nonlinear equation, which is what makes us a nonlinear system. And what I notice is because of this squared, I know that this graph is going to be a quadratic graph, so I know it's going to have that U shape. I also know, because this value out in front here is positive, that I'm going to have a U shape that is opening upwards. And I also know that because of the way this is written, that this is written in vertex form, and I can easily identify my vertex. Remember, in vertex form, we have A, H, and K, and our vertex is the opposite of H, which is 4, comma, K, which is -5. So I'm going to create a table of values for this quadratic so I can get a feel for where the points are and where this graph is going to go. Now, what I know about this vertex point is kind of like the middle point where it changes direction. So I'm going to plot that at 4, comma, -5, so right here. And I'm also going to put it in the middle of my table because I want to find some points around 4, comma, -5. So I'm going to do a couple of points on each side. I'm going to pick 3, 2, and 1, and then 5, 6, and 7. And what I remember about quadratics is that they are symmetrical. So if I can find points on one side of that 4, I can then reflect it onto the other. So I'm going to start with the x values closest to 4. So here I'm going to start with x equals 3, and I'm going to substitute that into my equation here. And then I'm going to figure out what the y value is when x is equal to 3. So here I have my y value equals 2 times 3 minus 4 quantity squared minus 5. Well, I know that this inside here becomes -1, and -1 squared is 1. So this is really 2 times 1 minus 5, which is 2 minus 5, which is -3. So here I would have the point 3, -3. So I'm going to go plot that. X is 3, y is -3. And then I also know that this will reflect onto the other side, so it'll be 5, -3 on the other side. So I have 5, -3 here on this side. Okay, so now if I move on to the next one, I'm going to look at the point x equals 2. So I have y equals 2 times 2 minus 4 quantity squared minus 5. I know this part here, 2 minus 4 becomes -2. -2 squared is 4, so this becomes 2 times 4 minus 5, which is 8 minus 5, which is a +3. So I know that x is equal to 2, and then y is equal to 3, and then I know that reflects onto the other side, so we also get x is equal to 6, and y is equal to 3 there. So we can go plot those next points. Okay, then we'll do one more just for good measure. So here we're going to do y equals 2 times, this is going to become 1 minus 4 quantity squared minus 5. So we get 2 times, this becomes -3 squared, which is 9. And so then I get 2 times 9, which is 18 minus 5, which is 13. So this would be 1, 13, and 7, 13. And those don't really fit on my graph, so I'm not going to graph them. But I can now estimate the rest of this to be approximately this. So I've graphed my parabola, and I have this first one officially graphed. So now let's move on to this second equation. And this one I can see is linear because it's written in that y equals mx plus b form. So we have a couple of different options here. You can use a table if you'd like, or we can use the y equals mx plus b strategy that we learned in previous math classes. So y equals mx plus b, remember, has a slope here of m, so that's your rise over your run. And that is always going to be multiplied by x. And then you have a b value, which is your y-intercept value and is where you cross the y-axis. So here we have the equation y equals 2x minus 9. So what this is telling me is that I'm crossing the y-axis at y equals -9. So if I go to x is 0, y is -9, I can plot my y-axis, my y-intercept point. Now from here, this 2 represents the slope. So it's 2 over 1, which is our rise over our run. So we're going to go in the positive direction 2, and then we're going to go to the right, which is the positive direction 1, to find additional points. So we go up 2, right 1, up 2, right 1, up 2, right 1, and we can continue this pattern all the way through the graph. So we keep going up 2, right 1, up 2, right 1, up 2, right 1. So we have many, 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 many points if we use that slope and y-intercept trick. So now that we've finished graphing both, what we're going to do is we're going to look at the graph and we're going to find the point or points of intersection where the two equations cross. And what I notice here is there are 2 points of intersection where these two equations cross. So I'm going to give me some room to write down my answers here. And what I notice is that my first point occurs at x is 3, y is -3. And my second point occurs when x is 6 and y is a +3. So these two coordinate points where we have x is 3, y is -3, and x is 6, y is 3, if we were to take these 2 points and we were to plug them back into these two original equations, what we would find is these are the 2 points that make both of the equations true. So we have found our 2 solutions, or our 2 points where the graphs cross. So let's try a second example here. So again, we see that we have a system of nonlinear equations because this first equation right here, due to the x squared, is going to be a quadratic equation. And because I can see I have a positive a value here, I know this graph is going to open up. But unfortunately, this one is not written in vertex form. It's written in standard form. So we're going to have to do a little bit of extra work in order to find our vertex point. But if we think back to when we graphed quadratics, we know that our axis of symmetry can be calculated by taking -b over 2 times a. That's how we find our axis of symmetry, which can then help us to find our vertex. So if we find our axis of symmetry here, we take -6 over 2 times a, which is 1. So we get -6 over 2, which is -3. So I know that my x value of my vertex point is going to be a -3. And then what I can do from here is I can calculate the y value for that vertex point. So we have this equation right here. So I have y equals, I can take -3 squared plus 6 times -3 plus 4. So this I get 9 plus -18 plus 4. So this becomes 9 plus -18, which is -9, plus 4, which is -5. So I know that my vertex is occurring at x is -3, y is -5. So I can plot that point right here. And then I know that that point is going to go in the middle of my table. So we have x is -3, y is -5. And what I'm going to do is I'm going to find some points around that. So I'm going to focus on -2, -1, and 0. Then I'll do -4, -5, and -6. So I'm going to give myself some room to write here. I'm going to calculate these one at a time. And remember, because of the symmetry part of this, we can actually reflect this over to the other values once we've calculated a couple. So let's start with y equals -2. So we have y equals -2 squared plus 6 times -2 plus 4. So -2 squared becomes 4. 6 times -2 is -12, and then plus 4 more. And if we add those together, 4 plus -12 is -8, plus 4 is -4. So we get -2, -4, and then we can reflect that over to get -4, -4. So if I go to my graph, -2, -4 is right there, -4, -4 is right there. Then from here, we can calculate our next point. So we have y equals -1. So we have -1 squared plus 6 times -1 plus 4. Well, negative 1 squared is 1, plus 6 times negative 1 is negative 6, plus 4. Well, 1 plus negative 6 is negative 5, and negative 5 plus 4 is negative 1. So we have negative 1, and negative 5, negative 1. So we can record those onto our graph as well. And then we'll calculate one more, so we're going to use 0 here. So we have y equals, this becomes 0 squared plus 6 times 0 plus 4. Well, that becomes 0 plus 4, which is 4. So we have 0, 4, and then we reflect that, we get negative 6, 4. So if I go to my graph, 0, 4 is right here, negative 6, 4 is right here. So now I have a pretty decent graph here showing me that quadratic. Okay? So then from here, we're going to graph this second equation. And I know that you may not be sure what this is. This is actually a line as well. So even though it doesn't contain an x value, this is a special type of line. And I'm going to use a table to model what's happening here. But what this is really telling you is that for every point on your graph, y absolutely must equal negative 1. And because there's no x value, it's basically saying x can be anything. We don't care what x is. We just care that y is always negative 1. So if we have y is negative 1, y is negative 1, y is negative 1, and then we pick any x value. So say I picked, negative 8, 0, and 8. So if I go plot these points, x is negative 8, y is negative 1 is right here. X is 0, y is negative 1 is right here. And x is 8, y is negative 1 is right here. So here I can see what's happening is I have a horizontal line here at y equals negative 1. And now that I've graphed both of these, what I'm looking for here is I'm looking for the point of intersection. I'm looking for a point or points where these two equations cross. And what I notice is I have 2 points here where this crosses. I have the point x is negative 5, y is negative 1, and I have the point x is negative 1, y is negative 1. So if I take both of these points and I plug them back into these two original equations, I will find that these 2 points are the 2 points that make these two equations true, and that's why they're the 2 points where these two equations cross on the coordinate plane.